All right, we got like three somewhat unrelated things to go through this video. Try to get through them as quickly as I can right now. So we're going to look at the idea of what a fuse is. We're going to look at some images or some symbols that you'll see uh, in circuit diagrams, and then we're going to look at how to calculate things on power grid. So hopefully these are fairly simple things for us to do. We'll talk about fuses, circuit breakers, and a kilowatt hour, which is probably a little bit new to you. So there's a couple of safety things that we have around us that kind of keep electricity from causing fire, causing damages. When we've done some of the labs and activities in class, hopefully one of the things that you've recognized is that it's possible for too much electricity to be going through a wire. So there's a couple of things we have. One is a fuse. And basically there's some pictures right here of a fuse, and you can see that there's two pieces of metal. What they do is the electricity flows through the fuse, so it flows from one side to the other. And the two pieces of metal are also connected by metal. Effectively, that if there's too much electricity that goes into it, the metal is going to melt. And once the metal melts, it kind of breaks the wire, and the electricity can no longer flow through it. As long as the electricity is flowing at a constant rate that it needs to be, the fuse is going to work properly, and the electricity is going to work. So typically, the images that you see here in the bottom, the most common place I've seen fuses like this will be in a car. Another type of fuse you see over here on the right hand side. Notice again, it's got a bunch of wire in it, but they work the same way. The downside of a fuse is, excuse me, once the fuse is broken, you have to replace it in order for it to be able to work, because it's basically destroyed at that point. You can't fix a fuse. You're going to have to be able to replace it. So it's kind of like a switch. Same thing with a light switch, turn it on, turn it off. But once the fuse breaks, it's permanently off until we get it fixed. Okay. So again, this happens because, as we've kind of gone over before, and we'll get into it a little bit later if we haven't, there are certain circuits that when we turn too many things on, you may get an overload of current. So this is a safety feature that we have in a lot of places. Our older houses used to have fuses. Now we have circuit breakers, which look like this image on the right-hand side. I discussed this in various times up to this point, but it's similar to fuse, but they don't have to be replaced. So we have these in our house. Typically, each switch kind of controls a portion of your house, a room, or section of the house. And if you turn too many things on in that room, it may cause too much electricity to be trying to go through the wire leading from each of these switches. And if so, then it's going to cause the switch to close up. Too much current is going to cause a break in the circuit. Unlike a fuse, these don't have to be replaced back out in general. Sometimes they have to be replaced, but most times you just go back in and you just flip the switch. Now, again, if you don't turn things back off in the room where the circuit broke, it's very likely that it's going to trip again. Sometimes we call it tripping the breaker. This might happen like in your kitchen if you got the stove on, you've got the microwave on, and you turn something else on. There's just too much electricity coming through the wire to be able to power all of those things. It gets too hot, and the circuit breaker is going to switch on, and everything in the kitchen would turn back off. So you can come back and flip this on, but again, you probably need to turn the microwave off or the stove off or whatever. Okay. So moving on to the second thing, and you've seen a lot of these pictures. You need to be able to recognize what these symbols mean. Hopefully at this point, you kind of recognize what some of them mean. Probably pause for a moment right here and maybe sketch these out or just write them down, particularly the ones that you don't know. You need to be able to recognize in a circuit diagram what the battery looks like, which is these two lines that are parallel, but one of them's shorter than the other one. Hopefully know what the wire looks like. Bulbs are usually represented by a circle with an X through it. Other resistors, I've got them down here on the bottom right-hand side, can be these like zigzag lines. And again, a resistor is anything that's going to be using the electricity. So specifically, if it's a bulb, like a light bulb, it might be represented with the X. Any other kind of resistor might just be represented by either of these symbols. Probably never going to see a buzzer. If we put a motor on something, we'll usually label with an M. And then sometimes a diagram might have switches on them. Now, if it's opened, that means the switch is turned off. Hopefully that makes sense, because you can see if it's open, the electricity can't flow through it. And if electricity can't flow through it, it's going to be off. In order to turn the switch on, we need to connect the wires And so when we turn the lights on, effectively, this is what we're doing with those. So I need to be able to recognize these. So any ones that are a little bit unfamiliar to you, make note of them, jot them down, do what you need to do. All right, moving on to the third thing, which involves a little bit of basic math, is talking about how do we calculate the power cost of something. To me, this is one thing that's super simple, but it can also be really confusing because of the terminology that's in there. Because in order to calculate the power cost of an object, we need to know three things. And so we'll go through how to get through this. So one of the things about power is, remember, power is current times voltage, I times V, and power is normally measured in watts. However, a power bill is based on kilowatts, and a kilowatt is 1,000 watts. So sometimes this is an important thing that we have to change, where if we've got an object that has a certain number of watts, like 100 watts, we need to change it to kilowatts, and we would do that by dividing by 1,000. So 100 watts would be 0.1 kilowatts. So anytime, again, I probably want to make a little note of this, anytime we go from watts to kilowatts, you've got to divide that number by 1,000. And then the other thing the power bill is going to be based on is how many hours of time that object is being used. So those are two of the three things we need to be able to do a calculation. So we need to know how many kilowatts the appliance is using, or the bulb is using, and how many hours it's going to be left on. So again, kilowatts, 1,000 watts. If we take the power and the time, that tells us how much energy gets used, which is most of the rest of the formula. But then what we do is we have to multiply that times the rate charge by the power consumed. Right? So we got three things going on. So like with our light bulb, if I kind of tie all this together, the light bulb has a certain number of watts. We would need to change that to kilowatts. We would also need to know how many hours the bulb is used. And then we would need to know what the power company is charging us. And for our purposes, we're going to say 10 cents an hour, 10 cents per kilowatt hour. And if we take those three things and multiply them together, that tells us the overall power cost for that thing. We'll do a few examples here in just a second. I'm going to skip through this slide because it's kind of confusing. So here's an example. I got a heater. I notice on this heater that's a 2 kilowatt heater, 2,000 watts. Could be the other thing that I don't know. If I run it for 3 hours, how much does it cost? So again, we got to do three things to be able to get the cost of it. So I've got the kilowatts, number one. I've got the time, which is 3 hours. So I multiply those two things together, and that gives me 6 kilowatt hours. And then the third thing I got to multiply by is how much the power company is charging, which typically is going to be around 10 cents per kilowatt hour. So if I multiply 6 times 0.10, that tells us it's going to cost about 60 cents. So not a lot. But again, for 3 hours at 60 cents, you did that every day for the whole month, it kind of ends up adding up. If we only ran it for 30 seconds, and this gets to be confusing, probably won't have any questions like this. Again, it's got to be in hours. So you have to figure out how many hours is 30 seconds. And that's a little bit confusing. It's not a lot of seconds, right? So 30 seconds, you'd have to do a little bit of math to figure out, how much of an hour is 30 seconds. It's going to be a fraction of an hour, right? So we have to do a little bit of math dividing by 60s in here. Don't worry about that part. Again, we're not going to have anything too funky about that. But again, it has to be in kilowatts. It has to be in hours when we do the math on this. So let's do a couple other ones where we don't have some crazy math into them. So if we had 4 60-watt lights and they ran 4 hours a day, how much is that going to cost again? So 4 60-watt lights, that if I multiply those together, that's 240 watts. But I got to move the decimal 3 places to make it kilowatts. So that 240 becomes 0.24. If I did it 4 hours per day, and we're doing it for the 30-day month, again, that ends up being 120 hours for the month. So we need to pay attention to, the time aspects that we have in here. So 4 hours a day, because it's every day of the month, that ends up being 120 hours total. So that's my total kilowatts. That's my total hours. I multiply those together. That's my total kilowatt hours. We would just multiply that times our 10 cents, and that would tell us how much it costs, which should be like $2.88. If we did a television, if it's 50 watts and it was 5 hours a day, Again, so 50 watts, we're going to move the decimal back 3 places, so it'll be 0.05 kilowatts, which is 5 hours a day, every day for the month. That would be 150 hours. So 0.05 watts, excuse me, 0.05 kilowatts times 150 hours would give us 7.5 kilowatt hours. If we had our heater, like in the previous example, it's a 2 kilowatt heater, and we ran it for 3 hours a day. Again, 3 hours a day every day is going to be 90 hours. 90 times 2 is going to be 180 kilowatt hours. So if each of these was at 10 cents per kilowatt hour, this would end up being the cost of each one of these. So the lights would be $2.88. Because again, move the decimal back 1 place, basically is what we're doing with these. The TV would be 75 cents, and the heater would end up being $18 a month for that. So again, 3 things: kilowatts, hours, rate. Kilowatt hours and rate. We do all 3 of those things. That's going to get us the cost for what's going to be on them. Okay. Sample problem, do a couple of these. Look to finish up. Samson washes his hair every day, spends half an hour drying his hair with an electric hair dryer. And the hair dryer is 1.5 kilowatts. So how much is this going to cost for the month? So actually it says how much is he spending on his hair each week. So our time is 0.5. I neglected to take into consideration the week on here. So there's he's doing it half an hour a day. We need to multiply this times 7, right? So that would end up being 3.5 hours for the week. So excuse me on that. So 0.5 times every day of the week. So 0.5 times 7. Power is 1.5, and the rate is 0.1. So you'd multiply all those together. And again, you would multiply these 3 numbers together because, like I just said, this 0.5 should be multiplied times 7. So that would give us the total number of hours. If you multiply all those together, that should give you your complete rate for that one. Right. And it's going to be the last one, I'm not sure. 4 kilowatt cooker is used for 30 minutes. If it costs 10 cents, what's the cost of using the cooker? So again, we need our time. Time is going to be half an hour. 30 minutes can't be minutes, it's got to be in hours. So 0.5 hours. The power is 4 kilowatts. The rate is 0.10. And we're going to add all the, multiply those 3 numbers together, and that will tell us the overall cost of using that cooker. So again, when your power bill comes to your house at the end of the month, it's basically all of those things that are using power kind of being combined together to get that rate, but you can get an idea of what it costs to use an individual object over a certain amount of time. All right, so I do think this is the last one. So again, 3 things. We need kilowatts, we need hours, and we need a rate. So in this one, it's 120 watt blanket, but remember, we're going to have to change this to kilowatt. And this is also saying 8 hours for the entire month. So we got to figure out how many outcomes, total hours that is. So our time is going to be 8 hours times 31 days to give us the total number of hours. Power is going to be not 120, but 0.120 because we're going to do it in kilowatts. And then our rate is 0.10. That's going to tell us how much it's going to cost per kilowatt hour. So we do all that multiplication together, and that should give us the overall cost of that. All right. So again, 3 things. We talked about the difference between circuit breakers and fuses and how they can be safety measures, some of the symbols that you're going to see in your circuit diagrams, and then again, how to calculate the cost of power. We'll have some example problems for this to be able to work through. So if you have questions, please ask.